Hello, everyone. I'm Corey Whitney. I'll be speaking to you today about probabilistic tools and their application and limitations in agroecology. We'll be working on one problem today, which is about operationalizing agroecology in development-oriented research, given system complexity and uncertainty. So I'll do three things to structure that today, three different parts. First, I'll outline the issue of causal ambiguity and the role of probabilistic models. Second, I'll show tools to deal with that ambiguity and walk through some of the processes. And third, we'll examine together this thing, which is where these tools hit limits and where they stop being informative. And the goal of the talk will just to be to show the changing role of these tools as uncertainty deepens, from inference to robustness to coordination. So let's get into decision making in agroecology and talk about plausible but competing investment pathways as a thought experiment to get us in the mood, to get us started. Imagine we have a public investment to make and to improve local value chains. We'd like agroecology principles to be made into food system interventions, to make it into those outcomes related to ecology and society from agroecology. So we are making this investment. It's possible in pathway A, I'll express here, it's possible that our investment builds trust and this trust increases price stability. Of course, with price stability, we expect these typically volatile markets to become stable markets. And therefore, if these markets are stable, we expect to see much better outcomes in terms of ecological and social outcomes of agroecology. But it's also possible that our investment builds trust. We have those better networks, really good connections, great interactions, and really good contracts and everything between all the actors along the value chain. Everybody's well connected and the trust is really built up well. But it doesn't actually affect price stability because it's not actually a driver of price stability as much as we thought. Trust doesn't cause price. So it's the same investment, but it works only if specific mechanisms work, only if it propagates in the way that we expect. So it's the same intervention, evaluated on the same data, but it can support opposing investment pathways. It's not just noise or uncertainty, but it's different causal stories are consistent with what we might observe. So the hidden assumption that we usually make is that the dominant causal story is known well enough to optimize under it. But I'm going to try to make the case here that when we're in this decision point, actually, we need to consider different causal stories. So in risk analysis, there's a powerful way to think about this, the value of information. It's a way of making modeling accountable to decisions. And it asks the question, should we act now or should we learn first? If we act now, we get our expected value under current uncertainty. So we could go ahead and we have some kind of distribution related to our expected value. We'll call that X. We could spend some time learning first, then depending on the opportunity cost of that time plus the cost of whatever research we do, we could get a new expected value because we choose a better action. We may choose a better action because we have reduced uncertainty. And the question that value of information helps us to answer is that value gained, Y here, that new expected value, is that more than the current uncertainty, the current expected value, and is that more than the cost that we would spend to get this? It's a way of comparing uncertainty or comparing outcomes under current uncertainty with outcomes after the uncertainty is reduced. It's a prioritization heuristic, and it helps us to make it explicit what's at stake when we decide. So instead of doing better prediction, finer parameter estimates, we focus on decisions that might change. And the hidden assumption is that the causal structure is well known, well enough to evaluate outcomes. And everything that follows in this talk will be about what happens when that assumption is false. Now we're going to step back a little bit and talk and zoom way out and talk about why probabilistic modeling and value of information is useful in agroecology or may be useful. And I'm going to make the case here that it's a useful approach because agroecology is nonlinear and their complex adaptive systems. So I'll lean a little bit on Holling's work here and show a model related to complex systems and talk about the phases. So in Holling's model here, we're looking at complex systems moving through phases. They're not static. And so noise we see within data this variance may actually be some kind of movement, a signal that the system is reorganizing rather than variance around a stable equilibrium. Levin and colleagues have generalized this insight in a lot of different ways. Here's a very simple model, but essentially showing how complex adaptive systems are made up of these nonlinear interactions, and that emergent behavior is the important condition here. We have a lot of emergent behavior happening in these complex systems, and so outcomes that we see can't be inferred from any components in isolation. Bowden shows us why. The outcomes emerge from networks of interacting social and ecological processes. This is a model from Madagascar on kinship ties and ecology. And they make the case that effects actually propagate through the whole network, not along a single causal chain. Most of our decision tools assume linear causality, but agroecology is different. And an intervention in one place can propagate through the system. And so what can happen is that linear logic can become unreliable when we're trying to identify the effects of our interventions. So to bring that home, here is the famous book by Morgan and Henrian, really important part of this whole thing. They work mainly in policy, but they make the case that actually uncertainty is not a temporary data problem, but a permanent structural feature of decision making. And so modeling, when we do probabilistic modeling, when we model these systems, it's not about making predictions, but it's about making uncertainty explicit and using these tools to structure uncertainty when determining expected value.